Hello and good afternoon, everybody. Bonjour tout le monde. So my name is Richard Pazer, and I will be your host for today's virtual rubber seminar. I'd like to welcome all the members of the Rubber Chemistry and Technology Division, and also our affiliated groups. We have the Ontario Rubber Group and the Quebec Elastomer Group, which are very active here in Canada. I'd also like to welcome all members or all people coming from outside of Canada. Thank you for coming. I hope you're going to really enjoy today's presentation, because today we're really excited to have someone coming from Europe. This is our fourth virtual seminar. And for this fourth one, we have a very special guest. We have Dr. Graf, who is probably well known amongst at least some of you anyways, especially in Canada, because he had spent some of his career here in Canada. And Dr. Graf is going to be talking to us today about how to optimize our rubber compound formulations. Okay, that's always a problem for a rubber compounder. And he'll be talking about artificial intelligence, design of experiment, using one or the other, or maybe a combination of both. So we'll see what he has to say about that. So Dr. Graf, as an introduction, he has a very long bio, very impressive. I won't give all the dates out, but he has his PhD from the University of Freiburg in Germany. And then afterwards, he has a very storied and long history in the rubber industry, starting at the rubber manufacturers in Germany, then going to Desma, and then going to Rhein-Chemie Lanxess in Germany. Then he made the hop over the pond to come to Canada, and that was in 1997. And he was the director of materials at Cooper Standard in Stratford, Ontario. He stayed there for 6 years and decided to go back again to Germany, where he took an appointment as a senior manager R&D polymer materials at Woco company. He has over 60 scientific articles and presentations, 25 patents. He received in 2012 the Erich Conrad Medal from the German Rubber Society. He is now a consultant. So his company is the HJG consulting firm that we would say here in North America. I know in Germany it's pronounced a bit different, but I won't say it here today because I don't want to look like a fool. So without further ado, I present Dr. Graf, so Hans, and the talk today is artificial intelligence versus design of experiments in rubber compounding. And I'm going to mute myself now. If you have any questions, please put them in the chat and we'll get to them after his talk. So Dr. Graf, the floor is yours.
Richard, thank you very much for your kind introduction and welcome from my side to all participants to this seminar. And I hope we have some good time to share and some findings or that we have learned at the very end. So my first slide to introduce us in the topic is that even before I had my first desktop, you read here a sentence from a European Rubber Journal, and that means tomorrow's machine will think for us. They may even tell us what to do. So that's a sentence, yes, really, you say, wow, that's a sentence. And then in 2015, there is John Brockman, when I try actually to dig deeper into this type of topics, then there is a sentence at the very end of this book where a lot of people get asked, what do you think about those artificial intelligence? And he said, tomorrow thinking machines will be very similar to today's old algorithm running on faster computers. And I said, wow, that is another sentence. Really get you probably down to the earth, I would say. Okay, the content of this presentation, a little bit an introduction, what type of tools we have today using actually computers. So we are now 30 something years in a computer age. And then what we really need to think about is what type of advantages and limits we have. And then we want to do a comparison and conclude something. So from my side, when I started actually was that type of topics more intense and try to use those machines helping me in my daily work. There is a Bridgestone patent, which from my perspective is maybe the oldest in '94, dealing with the exact same topic. Now we are rubber people, and it deals with how we can do more sophisticated compounding or make our work somehow easier. And even they made a second in 2002. And you see here other companies as well with some different approaches. And they actually, there's all formulation, mix something together and then have properties at the end which fit your needs. So, and before we talk about something, I hope we are feeling that we are engineers. Yes, there should be a definition. Then we have the same ground to talk to each other. And here you see some definition of statistic experimental design. And what is important here, that is not to do a formulation or something like that. Is an efficient procedure for planning experiment, nothing less and nothing more. So you can do a number of experiments and then draw valid and objective conclusions. Yeah, not biased conclusions, for example, if you think about that a little bit. And it is very helpful for engineers because normally we are working with small samples, either with a couple of rubber compounds, or we're working with procedures in the processes we have. So that is all a limited number. We are not in recognition of faces or something like that. Yes, as you know, which millions or billions of data. So and what we are doing with this type of methods is nothing else that we first create an idea that we name hypothesis. And that is our brain working, hopefully, yes? And then we evaluate this idea with a procedure in a systematic way that we are able to analyze. So creative I can be as whatever I want, and I cannot interfere with the design because this is a procedure needs to be followed. And then the analysis should be in that way that you try all to do to reject your hypothesis. That's very important to prevent you from being biased. And then you have all the statistics and things like that. So then what's artificial intelligence definition? So I Googled, and then you see when you read that here, is a theory and development of computer systems. This is much more fuzzy than we had that before. Yes, and then we have this here target as visual perception, recognition, decision making, and things like that. Yes, and then we have the so-called deep learning. is a subset of machine learning that enables computers to solve more complex problems. And then we have the so-called neural network programming. I'm now a little bit more specific, which you have artificial neural networks and or simulated neural networks. And we come later to those type of algorithm behind that. So, and what we have today now, today we have at least a software tool, for example, this compounding software. And we need to see that this is database oriented. And for me, database oriented is always, I'm looking backwards in my history and the way I created data and the time I have created data. So, and what the driving force was that we should utilize our history to make good decisions. In this case, for example, on compound or how we develop compounds in the future. So, and of course, there is a lot of pressure always on the compounder that it should be faster. And such software should help increase the creativity through a type what we call mostly simulation. So I want to have the computer calculating something, and then with those results, I will then save time and effort in the laboratory, for example. So, and when I do an experimentation and dealing with a procedure as design of experiment is, then I looking forward in the future. I have, for example, a new material. I have no data. I have no history. And now I want to use this procedure to learn very, very fast about the usage and the advantage of this new material. And this I do in terms of correlation of factors, that is our input, for example, our ingredients, on responses, that is our outcome, our effect of the ingredients and ingredients variation, and that are the physical properties. And all what I'm doing here should be on a safe statistic ground. And that means what I have investigated and evaluated yesterday should be the same tomorrow, even if that is then reproduced in another laboratory. So we have software tools in compound development, and that is the experimentation oriented. And again, we have the factors. We do that systematically. We test and then we treat those data with analysis of variance, that is ANOVA, regression, correlation, and things like that. We are aware that correlation is not chemistry or engineering laws. It is still a correlation. And I have to line up this correlation with the laws I have learned in school and the natural laws and chemistry and physics. So in the output, when I have done my trials, I've analyzed them. Yes, there are tools in those software where I can use for prediction inside my experimental room. And I can do overlay plots. I can look for contour plots and correlation maps and all the tools I have here for analysis and things like that. And what the math behind that is what we call regression. And regression can be simple, that is first order regression. Y is AX plus B or A0 plus A1 F1. or if I have a maximum, should be at least a second order regression, or if I have an inflection point, it should be a third order regression. And I'm fitting those data to my regression function. So I'm, in terms of an FEA guy would say, I'm smoothing the data. So how does that work? You see here an example of taken from the old compounding table. And that is, you have here a simple compound, you do a carbon black oil variation. And when you decide 55 pHr and 10 pHr, then you get results. And 71 Muni, for example, or 60 Shore as a leading parameter, and a tensile in the area of 21 megapascal. And you see here in a contour plot, and you see that is this point here. And the smartness is, this is done in the time before we had computer, all calculated by hand as far as I know, is taken from the Cabot compounding tables, which you will hardly find today. And that is still the basic of compounding, which we rely on. So, and of course, when you look at processes, you do the same. Yes, you have here an example from injection molding. Yeah, I want to have know my operating window of the machine, and you can do with a statistic process model in a very short time. Actually, for this type of experiments, you need 9 experiments for a fractional factorial design, and you can do that in 1.5 machine day, which I did in a large scale. Yes, and then you have all the influences of the process on your properties, and you can easily design your process that way. For example, the objective is always to find the shortest possible cycle time. And you see here one example, which is also made on a large scale machine, in this case, an LWB Steinel machine, where the nozzle opening represents somehow the mass temperature. And you see here, you can either close your operating window, or if you go from this size, you can open your operating window and have in a possibility to select the very shortest and energy efficient cycle time for your machine. So that is really, I think, some sort of procedure which is easy to follow, and it gives you a lot of benefit and advantage. So, and I don't need to really stress that. You can do the same thing in extrusion as we did in a larger project, which we performed in standard products at this time. And you see here a similar thing in an operating window type of manner. So when you go further, you see that you have good tools to check out whether your work is okay. So no big measurement errors, no problem in performing the experiments. You can do that easily with those correlation diagrams and see how the data fit on a regression line. Yes, and you can prove that everything follows the inherent logic of the rubber principles. You can do histograms, you can do scatter plots, and since sometimes you can do even contour or those type of correlation in 3D. You can do desirability plots and check whether the target is met, or if you fail something. And as I already said, you can also do prediction. So, and what we have, again, coming back to the regression equation, I have here written this regression equation in a little bit other way. And when you look at that, you have here the response column, the intercept column, and the factor column F1 and so far. And when you do that, yes, then you keep this picture, please, in mind, because we need that later when we go to artificial intelligence math. Yes, so you see, what you see here is a matrix of factors, yes, in columns, or if you see that as a regression equation in rows. And you see here a screenshot of the program. So you have here your factors, you have here your responses, and when you change your factors here, you can make prediction on the properties, but all in your small experimentation room. That is, you cannot leave that, yes? And we're coming back to this sentence later again. And today that is all very comfortable and easy. So with that, I hope you, if you work with experimental design already, you will, for you is that not new, and for all the others, I think I gave you a small snapshot, what is behind that, what math is behind that, and what type of analysis tools you have. So then coming back to, or moving towards our second big topic, and that is AE programming. And we want actually to know what type of algorithms are using this computer guys when they talk about AE and making our brain fuzzy with all their wordings and things like that. So we had a newspaper, Heise, and my nephew, who is my IT expert, he said to me, here, look at this. I gave you a couple of links, and then look at that. And then I was overwhelmed to see really a programmer, as you have that in picture in your brain, yes, a little bit white hair and a beard and something like that. Yes, and then he talks about k-means algorithm first of all. And that creates clusters and calculates means, and then calculates areas which he can center, and then by reorganization and iteration. I said, wow, that's interesting. So and then we're coming to the second object that he said, yeah, and then you look a little bit around, you make your mind, which we propose a solution. And then the computer is doing with those genetic algorithm, iteration and mutation towards this optimum. So I let the computer now calculate something in iterative manner, and let's move him towards a solution, and that we do with a so-called fitness function. That's why we call this the fitness, the fittest will survive. That's why we call this genetic algorithm. And that's at least some sort of iteration with a sum of the least squares. I mean, you remember your old school math. So I said, wow, that's even interested. And then we coming to neural net. So I thought about, oh, these computer designers, they're doing type of chip and trying to manufacture a neuron or something like that. Oh, then he explains, okay, that's a little bit more complex. You calculate weighted sum, normalize them to emphasize or dampen the summons, and then you let them walk through layers and that you can do that either in one direction, which we call feed forward, and then if you have errors and you try to correct them all backwards, then you have a so-called recurrent neural network, which is a little bit more complex than the other. Okay, I said that's understood. So now let's put that a little bit, visualize that a little bit. So what I'm doing is I have my inputs with my weights. I sum them, put them summoned, yes, and then I have so-called threshold functions, because not everybody should go through my net, and then I have all these inputs, and then I do that layer 1, layer 2, and layer further down. And you see here T. Rashid, I lost his first name, Rashid. Neuronal Nets is a book in 2017. And in these books, everything is explained really step by step. And I think everybody who has looked at his school math will be able to follow that book. So if I can do that. So what he explains is, oh, all this is matrix multiplication. That is with the terminology of neural nets. So you have columns times rows. That is matrix multiplication. Yes, and I have that here written in that terms. That is my weight. That's my input. And so that's my matrix then. And this matrix is multiplied with a sigmoid function, which is written here to have that modified. And here I modified all the subsequence layer. And there's a program language, Python, I think, which is very standard in the meantime. I didn't know that half a year ago. Yes, and there you have codes, very easy codes to program those things. So I said, wow, that's great. So actually, what we do now in neuronal network calculation is we have the signals passing through a so-called neuronal net, which is nothing else than algorithm equation in terms of matrix math, and that is matrix calculation, yes? And then we can specify that more precisely, and then we have this programming languages specifically designed for those type of programs. So when we see that all now I'm turning to my rubber recipe and say, wow, yeah, I have ingredients and properties. And now you look a little bit different to your ingredients, because your ingredients are normalized to 100 parts. So in our recipe, how we see that, we have already a normalization. And when you further think about that, I hope you agree with me, yes, all what we do is we dilute polymer. That is what we call compounding, normalized to the polymer. So I have already did some of the jobs. You have read that before in one of the previous slides. Yes, the normalization part we already have done in our recipe. Wow, that's fine. So now I go and say, in visualization terms, I have columns of data. Yes, you see here that's a little bit doubled, or that is my recipe on top, and my properties underneath. And all those data sets in columns, I now want to move from first layer to nth layer to get some sort of result, and the fittest survive. Yes, that is my evolutionary algorithm, or my desirability function, or however you call that. towards the iteration and reinforcing dampening and treating the data towards a result. And that is what I want. Yes, that is my database. And this here should, according to my targets, my compound. So that is mostly, I have multiple targets. Yes, I mean, just looking at the hardness of something out of a database, that is no fun. Yes, so I have multiple targets and what we call actually specification. Yes, and then I have my data, and now I'm searching, and now the pain starts here. Yes, my database is historic and probably incomplete. So I have also to have some sort of organization about my database, which would be helpful. But first of all, I have my k-mean or my multi-objective algorithm. I'm doing then a numerical solution, and there is a helping hand that is so-called gradient walking methods. And that is if you have more than one maximum or more than one minimum, yes, you need to guide the solution towards the maximum, the biggest maximum or the deepest minimum. And that is, you do that with the so-called gradient walking method. And what the computer is doing, computer is fast, very fast today. The data are treated all at once simultaneously. So then you need to guide that towards the solution, and that's, as I said, the desirability function. And that calculates the distance from target in our program. So, and the output is a recipe with its properties. So then we have a problem which we saw in the past when we first tested one of the first programs on the market, dealing with, it didn't named it artificial intelligence, but it was called computer-aided design program. And we found out at this time that in a database, you can have errors and you have a mass which is very intolerant to errors. So in the specification for this software here, I wanted to backtrack to the original data used for the results. And that is a little bit opposite to all artificial intelligence programming. So then you can, of course, import, export, and things like that. So I will skip that a little bit. So what you see here is a screenshot. We will explain this screenshot a little bit in detail. Yes, you have the input window, you have the criteria window, and you have the output window. And what you can do as input, that you can have your data, that's your recipe with your properties. You have a code that you can organize your recipe in the way you want. You have your ingredients list, you have a cost column, density column, because you want to calculate cost per volume, cost per mass, and things like that. So then you have your criteria field, and you see here your min and max value, because similar to design of experiment, you cannot go outside your room. Yes, in this case, your data room. So you cannot target an value which is not covered by your data. So that is your min and max value, and then you can do a query. um, like a spec, lowest, lower value, upper value from 2, and then you can put a little bit guidance on that. That is, you can say, this is more important. So you put a weight on your term, and then in case on conflict, you need to have a decision element, what you prefer as more important, that we call that trade-off. And then you have your output field, and you see here already that you can do a couple of artificial experiments side by side to think about that, what the changes are. So then you have diagnosis tools. That's a frequency distribution of ingredients and properties. You can choose whatever you want, and then you have a frequency diagram as a bar diagram, which is automatically scaled according to the min and max value of the database. So and then you have further diagnosis tools, which you have today also in statistic experimental design software. And that is that you can create all type of correlations. So you can actually search for correlations. And here I have correlated tensile over elongation. And then you say, a little bit, I expected that because the influence on tensile is quite large. Beside the crosslink density, for example, or other things. And if you go to modulus over elongation, you see here that you have a very nice correlation, because modulus, you know, is somehow linked to crosslink density with the Mooney-Rivlin equation. Excuse me. So, and of course, you can do that in 3D. Now you see you correlate modulus and elongation at break. And when you look a little bit friendly on that, the cloud here, yes, and you see when I'm looking from the top, that is grown above this pattern, which we have seen in with the modulus and elongation. And this way, yes, you can make up your mind whether your databases is sufficient for those type of exercise or not. So now, how to do a query, as already said, you put in your min and max value, you put in your weight, you put in your trade-off in the conflict, and then you have two recipes side by side. Yes, and you see here similar hardness and different compression set, for example, or modulus. I'm not sure what that is at the moment. So then this side by side allows you to change here your query and see at the same time in your, what I call simulation, what really happens. And even you can put the costs here on. So, and then we need the human brain again. Yes. And that is now you have made up your mind and they said, oh, this is a good recipe. It's in line with my experience. This is in line with my knowledge and with my past experiments. So you can transfer this in your input window, and then you see that shows up as marked unconfirmed. And what I want now, and that is your knowledge, go ingredient by ingredient and eliminate nonsense ingredients or ingredient combination. Yes, you see here, for example, in this example, there's a little bit natural rubber 10 and there's a little bit natural rubber CV60. yes, or the majority, and that is obviously nonsense. Yeah, but because the computer cannot think that way as we think, so he is calculating something. Yes, so you need to correct that, and you should do that. And then after you go step by step, and that is from my side the smart thing, that I'm forced to think about every ingredient in this recipe here. Yes, and then I get a recipe now. I leave my properties that way, and then I go in a what we call confirmation experiment. Yes, and with this confirmation experiment, my expectation is that you have a match inside the 95% confidence interval, which is a little bit mostly outside the measurement error. So what we do is we have a multiple query, we have ingredients and properties, we can trace them back, we have outliers and their corrections, and we can do mergers, so we can get other data in, or we can eliminate, but at the end we have to confirm. So, and now I have the proof. Is that all correct? Let me jump a little bit ahead here and be a little bit shorter. I recalculated a design of experiment. The outcome is, you see here the result in the yellow field of the experimental design. And I see here in a flag position the solution given by such a compounding software. Then I have a larger set of data with an experimental design performed in '98 by my friend from DuPont, Roger Vara. And I calculated that, you see, with this large design, it's a little bit of problem in accuracy in the lab. Again, what here we have this yellow window with the solution according to the spec. And here you see the flag, and that seems a little bit far off, but if you read here the table, you see that is actually very close inside the measurement error already specifically for the properties. So, and then recently in an existing project, I had a chance to really predict something out of a database, and we do a repeat, and you see here the results from two compounds, number 1 and number 2, and you see here the deviation from between predicted and the test results. And surprisingly, the modulus 100 has a larger error, or whatever happened, I'm not sure, because normally I think the modulus should be measured very accurately. So what we have large amount of factors in design are difficult to handle and analyze. Yes, and then we have all the statistics. But the advantage of all that, what I'm doing here, and we see that in the old literature, is that we are on a statistic safe. Yes, what was true in the past is true today and in the future. We are able to handle new materials in a way that we learn a lot in no time. We have in process optimization, the operating window and process design. And when we deal with historic data, we have at least a lot of bars to jump over. That is, a measurement error is unknown. Incongruent values, maybe their raw material, are they properly stored in the lab? Yes, we know reality is sometimes different from what we think it is reality, but we can still work with that, and we can do multi-factor query and do type of compound simulation according to spec. And the calculation is done in multiple small steps, and the output, I think, I learned repeatedly, is quite accurate. So, and now when we go to, let me say, our modern thinking about AI, we have the challenges, and that is a so-called back propagation. And that's really a challenge, because in face recognition or in spell checking or whatever, what we have in phone is all based on artificial intelligence. I can make very fast corrections. But when I have a rubber recipes and should now go in a machine learning phase, yes, I have weeks to wait until I get my result. Think about aging 1 or 2 weeks, or a stress relaxation experiment, or dynamic experiment, or lifetime experiment, or things like that. Yes, so we have a lot of time consumed by the test. Then we have our database standardization, a lack of thinking that way. Yes, we are not systematic. We can call us creative sometimes. I call us a little bit unsystematic. Let's be friendly to us. And I would wish that we have more database standardization, how we do that, and that we have a convention, what data should be permanently measured and what data are extra in regarding the customer or the specifics of the products. Yes, and then I need to able to identify data errors, so I should have no handwork involved in data transfers and things like that. So, and the nerve cells learns via error, yes, to optimize the weighing and the values of the input function. And that's what we deal in machine learning with the errors, and then we do an algorithm to correct those type of errors. So as a conclusion, yes, I have a tool for cost estimation, and actually for a starting formula in compound development. If I'm running out of ideas, for example, yes, I can play a little bit around and build ideas. And I have then useful historic data, and I have my statistic experimental design. And as I try to explain, both methods have their justification and should be used hand in hand. And I try to summarize that in types of snapshot. Yes, you have your history, you simulate, you confirm, and you have your experimental design, you explore, you decide, and you conclude. So, and with that, I like to thank you for your attention, and hopefully triggered a lot of questions. And thank you for joining, and I hope you had some fun.
Okay, thank you, Hans. Now we're opening up the floor for questions. I noticed that we do have at least one question here in the chat. If there's any other questions, please throw them in the chat. This is a question from Thomas. Hans-Joachim with slide 22. So if you go back to slide 22, Hans. There we go. His question is, do the layers follow the logic of the production, like, for example, mixing, forming, curing, and testing, etc.?
In terms of mixing, yes. Yes, because we have a formula and we in a data stack. Yes, and now we treat them. So if you wish, yes, and that we cross blend all the compounds together. Like I would do that physically, that I take compound from 1 from shelf and compound 2 from shelf and go to my mill and mix them together. Yes, and that was what we did actually physically in the far past. Yes, when I started my career and I had to rush for a compound, for example, in a spot market for hoses. Yes, and I had one week for shipment, not more time. So in this case, yes, you don't think, you just take that from the shelf, what you have, and mix that together. And I did that type of mixing on paper first to see what I should correlate and what would be the outcome. And I can tell the outcome was all inside the measurement error in my expectation. So yes, you do type of mixing, yes, but you don't manipulate any other things, yes. And then you calculate the mean, for example, from those simple experiment, and you will be surprised how accurate that is. Yes, and we do a similar thing here in terms of little steps all at once.
Okay, thank you. I had a question about artificial intelligence, and you talked about historical data. And of course, in the compounding world and in the rubber world, rubber industry, compound ingredients are always changing. So I look at, for example, the polymer. Polymers evolve. Look at EPDM. We've got different catalyst systems. So then that give different microstructures, long chain branching, things of that nature. So some of the historical data that you may have is going to become invalid over time because you cannot get the same grade of polymer, and you have to put in some new polymers using new catalysis systems or whatever. So that's sort of a problem using historical information, don't you find?
My answer is, first of all, I did a calculation on a whole design with historic data. Data were from standard Malaysian rubber from the past, published in a rubber formularity index. And a friend made the design with his raw materials, which he had at this time in Thailand. So he used Thai rubber for that. Mm-hmm. And what was interesting, was everything was okay except the tensile. Yes, the tensile in tendency showed this same slope in a 3D diagram. Yes, but there was an onset to higher tensile. And I thought about that because we used even not the same mixing machine for that experiment. So you can make up your mind that way in your analysis, as you say, molecular weight shows up in a certain way. If it comes to synthetic rubber, it's a little bit easier because a lot of the parameters we target today in polymer development is towards processing and process design. And we still have the molecular weight as a main influence on physicals, and we have the long chain branching, for example, and the molecular weight distribution. We have a little bit less influence, but more on the processing then. Yeah, so we have, let me say, two views as a compounder, and that is the physical properties and the process. And yes, it would somehow show up in some of the experiments. Think about dynamics or lifetime experiments and things like that. And I said, with our knowledge, we should have today around our desk, when we do those things, those experiments, we should be able to analyze those type of differences and see the development and the changes in the polymer. And with a modern instrument like an RPA, yes, we can really look deep side in the polymer and see all those differences much more than we did with only the Mooney in the past. Yes.
Right. All right. Thanks, Hans. There was a follow-up question by Thomas for slide 22. Sorry to go back again. He asked,
yeah, okay.
what are the other layers coming from then? Because I think you talked about the one layer pertaining to mixing, I believe.
No, the layers are here is a stepwise procedure. Yes, that is a computer work. Yes, we ask the computer to go in tiny steps. So we start on that side with the blue ones as an input. Yes, and then we mix all data together in tiny steps. Yes, because we want to avoid some sort of big influence from nonlinear effects. That's why you do in FEM analysis, you do small elements, and we do the same here, we do tiny steps. So see that as step 1, step 2, step 3. Yes, in artificial design or neural network programming, we call that layer. But indeed, here and there, yes, it is a computer who is doing step 1, step 2, step 3 in calculation.
Okay, we have one last quick question from Stephen Yu.
Oh,
He
hi,
asked,
Stephen.
have you verified the property that your software predicts beyond your historical database range?
No, beyond the range, you cannot go out because you have no data to calculate with. That is number one. And inside those ranges, yes, I have done confirmation, yes.
Okay, perfect. Well, that's all the questions we have. I'd like to thank you again, Dr. Graf, for giving this wonderful presentation. Now we learned a lot more about artificial intelligence. Definitely more than, I mean, a lot of us know about design of experiment, but now artificial intelligence now should be part of our language when we speak about rubber compounding. Thank you so much again for joining us all the way from Germany, where it's already nighttime, I believe. So
it's dark.
It's dark there, right? Yeah. And just a last note that this is our last rubber virtual seminars for this year. We will start up again next year in 2022 in March. And the speaker has yet to be announced for that. But if you do have ideas, please drop me a line as well. So thanks again to everybody, and have the great, wonderful holiday season. Happy Christmas, and Happy New Year, and we'll see you next year. Thanks.
Okay. All the best from my side.
Yep. Bye-bye.
Bye.